So today I'm going to present my approach to the M3 final hackathon. So predicting residential energy consumption. And the core objective of this challenge was to develop a regression model that minimizes the mean absolute error between our predictions and the actual energy usage of households across the US. So we were provided with data from the RECS, which includes a wide variety of features from the region and climate to the type of heating equipment used. And my journey to the final solution was not a straight line. It was a iterative process of analyzing data, testing hypotheses, and progressively refining my models using advanced machine learning techniques. So you can see, first of all, here I loaded the data sets and verified the columns. And the next part is that exploratory data analysis and pre-processing. So I started by dividing into the data. The first thing I noticed when inspecting it was the presence of negative values in columns where they did not make sense, like -2 for heating equipment. And by reading the data dictionary, I identified these as placeholders or not applicable or missing data. So to handle this, I converted these placeholders into NAN values to ensure our model did not misinterpret them as actual measurements. And next, I looked at the target variable energy consumption through visualization. It became immediately clear that the data was heavily skewed. Most households have moderate consumption, but there's a long tail of extremely high consumption users. So this skewness posed a significant challenge for linear models, which often assume a normal distribution. So this is the part I did. And there's a heat map and also some box plots. So next was for feature engineering. I didn't just stop at the raw data. I created interaction features to capture more complex relationships. So for example, I engineered area per person, so the total square footage divided by the number of household numbers, and also rooms per person, so a metric indicating crowding or luxury. And these new features help the model understand the intensity of usage, not just the raw building specifications. But I didn't do them in this part. I did them in the later parts. So this part is just some uh, feature engineering I did, except those interaction features. So here it is. And then is model selection and the metric pivot. So in the initial modeling phase, I established a baseline using three algorithms: linear regression, random forest, and XGBoost. While random forest and XGBoost were performing well, I wanted more in diversity. So first of all, here is the part I did. These three models. And then I wanted more diversity, so I introduced two state-of-the-art gradient boosting frameworks, which is like GBM and also CatBoost. So these models handle categorical features efficiently and often provide complementary predictions to XGBoost. And at this stage, I tried a simple weighted ensemble, optimizing the weights of these four models. While it improved results, I think I knew we could go deeper. And here is the part I did about this part. And next up is advanced optimization. So the breakthrough in my analysis came from two major advanced strategies. So first of all is the target transformation. So remember that skewed target variable I mentioned. I realized that feeding highly skewed data into the models was limiting their performance. So I applied a log transformation to the target variable. This normalized the distribution, bringing the skewness down from 1.92 to minus 0.34. So this made the underlying patterns more easier for the models to learn. And of course, after prediction, I applied the inverse transformation to get back to the original scale. So let me find the part I did about the log transformation. So this is the part I just talked about light GBM and CatBoost. And I believe the log transformation should be somewhere close. Okay, let's just leave it there. And the second one is Bayesian hyperparameter optimization. So manual tuning or simple grid search was not enough. So I employed the Optuna, a Bayesian optimization framework. Unlike random guessing, Optuna learns from previous trials to find the best parameters. So I ran an extended optimization session with 30 trials for each of my top models. First, for XGBoost, it found a configuration with a high number of estimators, but a shallow depth, so preventing overfitting. And for LightGBM, it optimized the learning rate and feature fraction. And for CatBoost, it tuned the depth and regularization strength. So this rigorous process ensured that every individual model in my ensemble was performing at its absolute peak mm, capability. And yeah, here's the part about the log transformation and optimization about these three models. So XGBoost, LightGBM, and CatBoost. And next, finally, for stacking and conclusion, for the final submission, I didn't just average the results, I constructed a stacking regressor. So in this architecture, my optimized XGBoost, LightGBM, and CatBoost models served as the base learners. Their predictions were then fed into a ridge regression meta learner. So the ridge model learned how to best combine these predictions, effectively correcting the biases of the individual models. And to summarize, my final solution leveraged first one is domain-specific feature engineering, area per person, such as. And second one is log transformation to handle the data skewness. Third one is Bayesian optimization, which is the Optuna, for finding global optimal hyperparameters. And fourth is a stacking ensemble to combine the strengths of three powerful gradient boosting algorithms. This robust multi-layered approach allowed me to submit a solution that minimizes the MAE while maintaining excellent generalization on unseen data. So thank you for watching, and let me show you the final part of my code, which is the extended Bayesian optimization here and also the final summary. And that's it. Thank you for watching.